and welcome to the Convex Conversation with me, broadcaster Helen Fospero. More than 55 million people live with dementia worldwide, and there are in the region of 10 million new cases every year. Dementia is now a leading cause of death in the UK, but behind the scenes, scientists are working hard to detect Alzheimer's disease, one of the biggest causes of dementia, in its earlier stages, before symptoms show. The disease can start to cause damage in the brain years, even decades before diagnosis. To mark Dementia Action Week, I've come to meet an academic neurologist. Dr Dennis Chan is a Principal Research Fellow at the Institute of Cognitive Neuroscience based at University College London. UCL is number one for research in the UK and has produced at least 29 Nobel winners. His primary area of clinical and academic interest is the detection of Alzheimer's disease in its earlier stages, prior to the onset of dementia. Dennis, I'd just like to say thank goodness there are fine brains in our world like yours who are working on the detection of Alzheimer's disease in its earlier stages. How great a challenge is this?
Well, Helen, first of all, thank you very much for having this chat with me. I think I probably would take issue with your comment about my having a fine brain. I wish I did. But I take the point about good people working on this. It's a huge challenge. It's something we've become increasingly aware of over the last few decades. And that's in part due to the fact that advances in medical science mean that people are living longer. And as lifespan extends, then people with dementia, there are larger numbers because one of the greatest risk factors for developing dementia is age. And that's why we're seeing more of it. And given the severity of the problems and how much care people need when they have dementia, this is something that affects a lot of people, affects their families, affects their family's ability to work, affects health services, social services. The impact on individuals and also the nations is huge. And we're seeing this growing more and more and more. And I think that's why there's a larger emphasis in trying to understand Alzheimer's, dementia causes, and ideally find cures in due course.
It sounds like it's a great challenge, but I suppose at the same time, Dennis, this is a great opportunity, isn't it, for people to be tested and work out if you can see the effect of Alzheimer's years before they start suffering the symptoms.
Yes, I think that's right. If we're now in a situation where we're seeing the impact of dementia, i.e. what happens to people towards the end of the disease when they have a lot of problems, it's only logical to assume that if we can actually stop that happening and rewind right to the beginning, before people have dementia, before people even have symptoms and they're well, if we can identify that at the beginning with the hope and, dare I say, expectation that we are going to have more effective treatments, possibly even cures in future years, then it would be wonderful to think of a future world, future generations in which we would identify disease early, treat with suitable treatments, and people would then either never go on to get dementia or it would be so delayed that the impact on their lives would be forestalled and pushed back for many years.
So in layman's terms, can you describe how Alzheimer's affects the brain in those early stages before people even know they've got it?
Yes, I'll do my best. So we do know what Alzheimer's is to some extent. We do know that it's what we call a degenerative disease, by which I mean that the condition causes brain cells to be damaged and ultimately then to die away. And when that happens, then the brain doesn't function quite so well. And when that's taken to the extreme, that means that large parts of the brain don't work. People have a significant memory thinking problem, and that equates to dementia. But if we then rewind that clock and look at the basics of this, what we do know is that these degenerative diseases, like Alzheimer's, we know that they're associated with this buildup of proteins, so microscopic proteins within the brain. They're there anyway. They're part of our normal brain cell machinery, but somehow something goes wrong with them and they start accumulating and then clumping out within the brain cells and outside of the brain cells. And we know that that process by which these proteins start accumulating is somehow associated with damage to the brain cells. Now, we don't know why they accumulate, and we don't know quite yet how they cause damage to the brain cells, but we know there's an association. And then as that brain cell damage starts multiplying and propagating throughout the brain, then more and more brain systems start to become damaged. They then start to function less well, and that then causes symptoms. So in summary, what that means is we have some scientific understanding of the building blocks of what Alzheimer's and degenerative diseases are. We know there's an association with these molecules, these proteins that cause pathology. So there's a lot of lab work that's looking into what those molecules do, how they might start accumulating and clumping in the brain cells, how they might damage the brain cells. So if we know that's the case from the basic science side, and we know that ultimately years, decades down the line, that ends up with people having dementia, what we want to do then is we want to say, okay, well, can we then look for the very beginning of when people begin to have that brain change, that there may be some changes occurring in their brain. They're not yet aware of it. There may be before their symptoms, certainly before they have dementia, but essentially this will be sort of under the bonnet. So there are changes going on. People don't yet manifest symptoms, but they are going to. And can we identify that? Because if we then can, because we're catching the disease at the very beginning, then that maximizes the opportunity that future drugs or treatments might then be effective. We know that at the end of the condition, it's hard to treat dementia because by that stage, there's widespread brain cell death, there's widespread brain shrinkage, and there's widespread damage. It's very hard to reverse that. So we want to be doing it much earlier when there's a lot of brain that still works, yet to be damaged, and we want to forestall it and nip it in the bud.
Am I right in thinking that the part of the brain that it affects in these early stages is, this isn't a technical term, Dennis, is the sat-nav part of our brain that helps us with navigation and finding our way around?
We're pretty sure that that's one of the first parts. It's certainly the bit that we see the first degeneration. So it's this area within the temporal lobe of the brain, so-called because it sits behind the temples. And we know that that's an area that controls memory. And that explains why people with Alzheimer's, the archetypal first symptom is a memory impairment. And that actually is the main symptom throughout the condition. But that part of the brain also controls our, as you say, our sat-nav. It controls our ability to understand where we are, how to get from A to B, which is why getting lost is then another early symptom in Alzheimer's.
And in 2019, when you were at the University of Cambridge, you were featured on international news programs in The Times, the FT, The Guardian, talking about how a virtual reality test could help. Can you tell us a little bit about that testing you did on memory patients?
Sure. So because of this knowledge that this medial temporal lobe area is first affected, based on our understanding of what these brain cells in the temporal lobe do, and this goes down to the basic science of what the cells do, there's been a lot of work by people I've been very lucky to work with over years who studied how our brains tell us where we are at the level of the brain cell. And this for me has always been very compelling because the idea of understanding a behavior like navigating in terms of what individual brain cells do, it's quite extraordinary because most of the time when we do things like, you and I are talking now, if you said to me, well, what are the brain cells, what are they doing while we talk? My answer would be, I've got no idea because that's really complicated. So we have this window of understanding the cell basis of this behavior. And if that cell basis drives navigation, and this is the first part of the brain that looks like there's degeneration, we kind of wanted to test the idea that maybe then looking at people's navigation in early Alzheimer's disease might show there's an impairment and there's a change. But of course, testing navigation is not so easy. You can't do that in clinic. The kind of traditional pen and paper tests of memory that we do in memory clinics, you can't test navigation with that. It's not possible for me to send someone out in the middle of Shepherd's Bush and ask them to wander over to Holland Park. But VR turns up, virtual reality, and that's something I've been looking at for a while because the great beauty of VR is that one can simulate environments. They design it for games, that's absolutely okay. But VR for experiments is quite useful because we can generate environments, and it allowed us to test whether or not people with early Alzheimer's had an impairment in their ability to remember how to get from A to B. So my colleagues at UCL designed this VR test, and we asked our patients, long-suffering patients, who actually, I've got to say, they quite enjoyed it because it's very different to what they normally do.
Well, it's like playing a game in a way, isn't it?
It was great. And actually, funny enough, when we first did it with them, we had to change the VR game because my colleague at UCL who programmed it, he was a games designer, and he actually over-designed the test. There were loads of flying birds and trees waving in the wind, and no one would actually do the task because they spent too much time like staring around thinking, wow, this is so cool. It looks like Yosemite. And we actually had to dial down how visually stimulating the test was so that people actually did what we wanted them to, which is go from A to B. So we tested this VR in my patients with memory impairment, and they didn't have dementia, though before they had dementia. And we found that actually, if you have what we call mild cognitive impairment, which is this rather wordy term for that stage when you have a memory problem, but it's not so bad you have dementia. And we found that those people with mild cognitive impairment, and it was due to Alzheimer's, they did really badly on the test. Whereas other people with mild cognitive impairment, because memory impairment is common, who didn't have Alzheimer's, so in other words, the memory problem was due to getting older, stress, anxiety, whatever it is, but it wasn't Alzheimer's, they did fine. So this for us was really important because it showed A, that navigation was affected, but also B, that it could pick apart those people who were seen in clinic with a memory impairment due to Alzheimer's versus people with memory impairment not due to Alzheimer's, to us, that was important because every single day across the world, there are people seeing their GPs and doctors saying, my memory's not very good. Some of those people will have Alzheimer's as the underlying problem, and they will in turn, they're probably likely to go and get dementia in future years. But many of them won't because it's not sleeping well, or they're worried about the war or climate change, or they got apnea, or they got depression or anxiety, but they don't have it. And so we need better tests to pick up who actually has the beginning of Alzheimer's. And our VR was beginning to look at that.
And could virtual reality be used as a diagnostic tool in all sorts of conditions?
I don't think VR in its current setting will, because what it involved us doing was putting on a VR headset. Even though they're now smaller and wireless and so on, there's still a big bit of kit. But I think the underlying principle of what we're trying to capture can be detected, and that's actually work that my colleagues and I do now. So, for example, why do we measure navigation? Well, ultimately, it's because it's effective, but also it's because we all do. We all navigate. It doesn't matter whether or not we live in London or Adelaide or sub-Saharan Africa. All human beings navigate. All mammals navigate. And there are other ways to work out how to test that. So, for example, my colleagues in Cambridge have developed an app which can just monitor how people walk around just their normal daily life. Because what we would expect, something like that, and all we're doing is we're just letting someone do their own thing. There's no VR, there's no test. People don't come to my lab or clinic to have this done. We just say, well, you just do what you do. But actually, our hypothesis would be if someone has the beginning of Alzheimer's, the way they walk around is probably different. They may not know it, but they probably are. So when I'm trying to explain this, the analogy I come up with is almost like imagine the way you would get your supermarket. And probably if your mental map, your GPS was okay, you probably have a shortcut. You can go through the park or whatever it is. If you have something like Alzheimer's and your GPS not working so well because the brain cells are damaged, then probably you could still go to the supermarket, but you might go another way. You might think, can't quite remember how. I'm going to go to the Tesco's at the end of the street and turn left. So in other words, the way you get somewhere is different. But the person affected is probably not going to be thinking, my gosh, I've got a problem. I didn't realize this, but my navigational strategy has changed. But from a scientific point of view, we would know there was something different. That's the kind of under the bonnet thing I'm talking about.
So if you spotted some under the bonnet stuff going on, are there patients now being treated pre-symptoms, or are we not as far on as that yet?
There are people in trials around the world treated with anti-Alzheimer drugs, targeting these proteins I talked about to see whether or not they might work. We don't yet know the results of those studies. The idea is that in due course, as and when we have effective treatments, it would then be given to people with those problems prior to them having symptoms. So under the bonnet again, if you like.
I always feel that medicine's quite reactive. We have something wrong, we go to the GP, we get some treatment. How big a role do you think technology can play in our health moving forward and in medicine to make it proactive?
Yeah, that's a really interesting question. So funny enough, whenever I talk about this in lectures, I kind of put up two slides. I put up a slide of someone with their bonnet up and steam coming out of the engine saying, this is what we do in medicine now. The car breaks down, we then fix it. And then I show a picture of a snapshot of someone's screen with a sensor saying your tires are getting flatter. And I say, this is what we need to be doing, reactive. So you're right. Medicine generally, traditionally, is reactive. We wait for someone to have a symptom, because a symptom by definition is something's not right. They then go and see their GP and say, I've got a symptom. But that always means necessarily that we're behind the curve, because we have to wait for someone to have a symptom. So it has to be reactive. So you're quite right. We then have to think, knowing that there's stuff that goes on in things like Alzheimer's, before people have symptoms, we cannot wait for the symptoms because we know then we're behind that curve. Can we use technologies to look for changes first of all? And the reason why technologies have a great role in that is because they have the capacity to measure all the things we do in our life, be it the way we sleep, be it the way we talk, the words we use, where we navigate, how many places we go. We live in a world now where technologies, if you want them to, can measure loads and loads of different aspects of our behaviors and our functions. It is highly likely, if not sort of definite, that a lot of those functions and behaviors will begin to change before people are aware of it. So we talked about navigation. I'll give you another example, sleep. And there's a load of stuff about sleep and it's affected early in Alzheimer's, and it's a really complicated interaction. But of course, we can't measure sleep in clinic. I guarantee you that in Alzheimer's and actually other diseases causing dementia, which we've not talked about, there are things like Parkinson's disease, there'll be a change in sleep. So we absolutely know that. We can imagine a world in which actually measuring someone's sleep may show early changes in their sleep patterns. So for example, how many hours of REM sleep they have, or whatever it is. They're not going to know that because they're asleep. We don't measure it because up until now, we've never had any ability to measure people's sleep in their own homes. How could we? But we do now. So I think what technology does for me, it is a great enabler of things we want to do. I guess I just want to emphasize that point because when people like myself or others around the world use technology and we kind of look about digital diagnostics for all sorts of medicine, I think it's really important to not to fall into the trap of using technology for technology's sake. The fact that we have all these devices, kind of automatic idea was, yeah, okay, fine, got to use it, it's got to be great. And I'm not entirely sure that works. I think if there's a scientific rationale, like for example, sleep, and there's some sort of scientific reason why it will be good to measure such and such, then I think the technology then comes in. I'm less convinced. I know others might disagree, but I think it's more powerful if we have a good basis for using the technology. The flip side of that is artificial intelligence. The other way of looking at it would be to say, well, hang on. Well, there's a whole bunch of stuff that people do. Until now, we've never been able to measure it, but now we can. We can measure people when people walk, talk, sleep, etc., etc. Now we monitor all that and we collect huge amounts of data on all these people, and some of those people may have Alzheimer's, and some of them may have genetic Alzheimer's or Parkinson's, or whatever it is. And then we give it to the machines to learn and crunch through this, what they call big data. Then it might be that the machines or artificial intelligence might then pick out something, identify some mark of some signal of disease that we never knew existed. So we've talked about navigation because that's the temporal lobe that's affected early. And that's your kind of classic science-based approach. Have a hypothesis, have a prediction, you've got a rationale, test it, prove the hypothesis, great, and go on to the next step or whatever. The AI line of work is completely different. It's the opposite direction, which is to say, we don't have any hypothesis, just give us loads of data, and then we'll crunch through the data, and then the data will tell us there's something. Might do, might not do. Don't know what it is. We can be agnostic. We don't have to weight the dice, let the data speak for themselves, and then we're going to find something. And that's why we see a lot of AI in medicine now, because actually it has that ability to crunch through so much data, can generate things that your kind of traditional hypotheses didn't identify.
In a way, it sounds Brave New World, but then if you walk down the high street and see how many people are wearing perhaps a Fitbit or an Apple Watch or whatever, and are monitoring without even really realizing it. They're collecting, for example, their sleep patterns, but nothing's actually happened with it other than they might say to Joe Bloggs over a coffee that they'd had 4 hours of REM, but they won't really know what it means. But it is a wonderful source. If that can be connected to the medical world and be crunched, it's amazing what could come out of that, because we can collect so many things about our body already, can't we, just by wearing a watch?
Well, we do. That's already there. That's the world that those of us who are lucky enough to be able to have these technologies, that's already happening. So as you say, you're quite right. You can measure your heartbeat, you can measure how your heart rate changes when you stand up or walk around, or when you play a game of tennis, or how many steps you do. There's a huge amount of stuff in there. For me, it's not that far-fetched to think about a world, maybe not that far away, when actually, let's take something completely outside of Alzheimer's. Let's take strokes or heart attacks. And we know that's related to high blood pressure, and someone will go in and they'll have a problem and the GP will measure it. You can imagine that there might be a future in which people say, hang on, I'm going to see my GP. My blood pressure is just it's kind of cycling. I never did this before, but I'm kind of 5 points more in the morning. This is different, and they have no problems. But actually there is a subtle change because they're continuous monitoring, because of their apps, because they have an iPhone or whatever it is, it picks it up. People will be seeing their GP saying, listen, my heart app tells me my blood pressure is a bit weird. I'm completely fine. So as far as I'm concerned, do I need a checkup? And the GP will scratch their head, and most of the time they go, I don't know. I mean, it doesn't look too bad to me. As we go through the generations and as we see how these things unfold in all our big sort of studies and epidemiological population studies, we're going to understand more and more and more about what those signals mean and whether or not that's going to make someone at risk of heart attacks in the future or strokes or whatever it is.
We talked about the virtual reality test. What's your mind occupied at the moment? What kind of testing are you doing, and what's keeping you awake at night, Dennis?
Lots of things keep me awake at night, not much of them to research. But okay, so where we are now, what my colleagues and I have done recently, very recently, is just completed the next stage of study, which is to ask the question, is navigation affected in people before they have any symptoms? So we've gone early into the study, and actually this is something that we have actually just finished, and we're in the process of writing it up for publication. And this is led by my PhD student Coco Newton, who's in Cambridge. And it's really interesting. It's part of a national study called PREVENT, led by someone called Craig Ritchie in Edinburgh. And this is studying people who are between the ages of 40 and 60, the middle-aged people, they have no symptoms, and looking to see what changes in them and what may be indicative of future risk. So because they're 40 and 60, they're not old, but they're in that age of life when they're going to get old. And some of those people may get dementia. And what Craig and his team wanted to do was to say, well, if we do this study called PREVENT, if we look at these middle-aged people, what can we find are the earliest changes, or changes in maybe their brain function, their behavior, the scans, whatever it is, and that might be very, very much upstream of these people in the future getting dementia, because some of these people will be at risk. And there's about 750 around the people included in this. So it's a fairly decent sized study. And of those people, some of them will have a greater risk because they have a genetic risk from their DNA profiling, or they may have a family history of dementia. Because if they have that, then there's a slight, not much, but there's a slight risk. So again, these people don't have any symptoms. They're middle-aged, they have no symptoms. But some of them will have a greater risk of having Alzheimer's because of their genetics or family history, whatever it is, and others won't. And what Coco did for her PhD work was she applied that same VR test that we did in our memory patients. And it's really interesting. And it turns out that if you're at risk or not at risk, remember these people, middle-aged people, they have no symptoms. Your standard memory and thinking tests don't show any difference between the risk, high risk and low risk. And the only tests that look like there's a difference were our navigation tests and our spatial tests. And what we think that means, what that might mean, is that these people who are at risk, if they are actually not doing quite so well, that might be the very, very, very first signs that there is a problem. And that would be very important for Alzheimer's research and treatment, because there's a kind of tipping point. You can be at risk, but not have a disease. Being at risk doesn't mean you have a disease. It just means you're at risk. But at some stage, people are going to tip over from being at risk to having the disease. And we don't know where that point of inflection is. We're very familiar with doing it down the road when they have memory impairment and then further on when they have dementia. But that's the key point. How do you pick that point when you go from being no disease but at risk to beginning of disease? What we're trying to do in our work is to say, well, can we be driven by the science and the temporal lobes and navigation and all these cells and everything, and look for that first change? And this is what the PREVENT study is about, and that's what my colleague Coco Newton did, and that's what we're finding. So in summary, what it looks like we're seeing a really early change in behavior. Again, before people have any symptoms, they're absolutely fine. They're middle-aged. They're not the age when people got dementia. When they started the study, the people were an average 25 years younger than their parents when they had dementia. So we're not talking about years before. We're talking like 2 decades before they would be estimated to get dementia. 2 decades, actually more than 2 decades. But we're seeing some early brain changes. And we're not seeing it on traditional memory tests, the kind we do in clinic. We're seeing it on our tests. And that fits with what we think is going on, because we think that navigation, due to brain cells in the temporal lobe being damaged by these proteins, is going to be affected early. So we're kind of this point going earlier and earlier and earlier. We've done the study in people with memory impairment. They don't have dementia, they've got memory impairment. Published that, they did less well. So we say, okay, fine. Let's go further back before people have memory impairment. And that's the study. And then there's some other sort of cool stuff that comes out of that. And we're modeling the information now. And it turns out that when people can't do this navigation task, which is equivalent to dead reckoning. It's what mariners would say, dead reckoning. You start off somewhere, you go somewhere else, and you go back to the beginning. That's what the test is. And that's a really pure test of navigation. What we're seeing in these people in this PREVENT study is they can't get their dead reckoning right. They end up going to the wrong place. When we say to them, go back to where you were at the beginning, their error is greater than if you're at risk than if you're not at risk. And when we're sort of doing our modeling and looking at what's going on, it looks like what people are doing is that in their heads, they can't quite work out their angles to go back to the beginning, which is then, to me, really interesting, because that then says, okay, well, that's about how we then work out vectors in our head. And that is kind of nice, because what we're taking a complex behavior, getting from A to B, and trying to then break it down to the mathematics of what's going on. And once we start doing that, then that begins to give us an angle into fundamental building blocks of the behavior and the behavioral change that happens really early on. One of the reasons why that's really important is because if you do memory tests or thinking tests, there's loads of things that can influence how you do it. Like whether or not you slept well that day, whether or not you're worried about it, whether or not you've had a beer before or not a beer, loads of things. So one of the issues that's always been leveled against standard memory behavior testing is there's so many what psychologists call confounds. Oh, well, you can't necessarily attribute someone's bad behavior, bad function on this to that, because actually they're really stressed, kind of in a room with you being tested. Of course they're stressed. But if we're saying, well, hang on, but this is actually a basic fundamental calculation that our brain cells are working out vectors, well, that's less likely to be affected by things like, did you sleep well the night before, whether or not you're stressed, because that's a vector computation. And again, for me, it allows us to go back to the brain cells and to link the behavior that's changing in early Alzheimer's with what's going on at the level of the cell, because actually it's what's going on at the level of the cell which is being driven by the molecules. Ideally, we want to link that process that says, okay, you've got these molecules, these are proteins, and they do bad things to your brain. We don't know how, but they do, and that causes Alzheimer's. And then at the end of that, you've got the human being who's got a problem. Well, there's a huge ocean of understanding, a gap, a knowledge gap between those molecules that cause Alzheimer's or others that cause Parkinson's and the person who's seen in clinic with the dementia. And one of the reasons why we don't have any cures is because we don't have an exact understanding of what the link is between the molecule at the one end and the clinical manifestation, the memory impairment dementia, at the other. And if we don't understand those mechanisms, not surprisingly, we're going to have a problem trying to figure out the drugs to solve it. So if we can then join the dots by saying, okay, you've got molecules, they do bad things to cells, they damage the synapses, they damage the cell function, this is what the cells do. And then this is what the cells do as a group of cells, and they control a behavior or function, sleep, navigation, whatever it is. And then we find that's affected. Then we're beginning to say, aha, actually, we are now joining the dots. But that requires that central bit, the understanding of the cells and the basic properties to bridge that gap between the molecules and the behavior, because they're different dimensions of scale.
So what is it, Dennis, that drives you to navigate that ocean? And I suppose I'm really asking, what is it about dementia and this part of neurological work that drew you in the first place? Why this particular area of specialty?
I can answer that in two ways. I'm lucky enough to be a clinician. I'm lucky enough to have had a scientific training as well. So from a clinician point of view, it would be great if we had a way of treating Alzheimer's better than we do. So I run a memory clinic. I see people with lots of different memory problems, be it mild cognitive impairment through to people with established dementia. And it's really sad and upsetting when I see someone, I make a diagnosis and I say to them, like I did yesterday to somebody, okay, so I know what you've got and you have this and it's called a degeneration. And I kind of explain about brain cells and all that. And then I say, I'm really sorry, but I don't have a treatment. So as a clinician, you think, well, that's a basic failing because I'm kind of diagnosing, but I'm not doing anything beyond that. Okay, and we can manage and be supportive and we can use medications to alleviate sleep problems or whatever it is. The fundamental problem is that I don't have a treatment that actually is truly effective. So as a clinician, when that's our job in all ways to look after people, do our best to look after people, that's a huge gap in our ability to do the right thing. So as a clinician, simply put, it'd be nice if we had better treatments to stop people having Alzheimer's. And then as a scientist, I think it's also compelling because that point about fitting in those gaps from molecule to brain cell to behavior is a great scientific challenge. And I was lucky enough when I did my PhD nearly 30 years ago, I worked with someone who was studying how brain cells created navigation, created our GPS. I didn't know at the time because I was just an idiotic PhD student aged 19 or 20. But this was world-leading research. And actually, you talked about Nobel Prize winners. My boss, he's still my boss, John O'Keefe, is one of those Nobel Prize winners that you see on. He got the Nobel Prize for this in 2014. It's amazing, the idea of having an understanding at the level of the cell, individual brain cells, of something as complex as navigation. That's why he and colleagues of his got it. But when I was a student, I remember thinking, well, there's an elegance about understanding a complex behavior at the level of a brain cell. So when I then sort of went back after my PhD, finished my medical degree and whatever, went into neurology, you learn about Alzheimer's disease, and I didn't know anything about Alzheimer's at the time, but I did know it caused a memory problem, and I did know it affected the temporal lobe. So I kind of sat there thinking, well, hang on. So we know these areas of the brain. There are all these amazing scientists studying what these brain regions do at the level of the cell. And wouldn't it be great if we sort of design new tests to somehow utilize this elegant neuroscience knowledge that people have been using for 20, 30 years? Shouldn't we be somehow bringing that to bear into our clinical practice? Can we do that? And of course, the answer was no, because we didn't have any way of testing navigation at the time. But there was always that part of me that thought it would be great to join the worlds of neuroscience, cell-based studies, and the clinical world when people have a problem. Because we had that bit in the middle, because of the work of O'Keefe and others, that says, this temporal lobe, it controls navigation, it controls our GPS. These are the cells, this is how they do it. And for my world as a clinician, I'm thinking, well, this is exactly the same part of the brain that gets hit by first off in AD, Alzheimer's. And you sit there and you think, hang on a second, we've got to have a conversation about this. The people in UCL who designed the navigation task, they also are with Johnson. Neil Burgess is the lead, Professor Neil Burgess. And it's that sort of same principle. It's the idea of saying we have this really beautiful, elegant neuroscience, this understanding, pure science understanding, of trying to work out how the brain does what it does. In this instance, navigation. And then from a clinical side, Alzheimer's disease, this really important condition, biggest cause of dementia, causing no end of woe and problems for everyone worldwide, increasing problem. And this is where the worlds join. And as a scientist, it's wonderful to have the opportunity to speak to these different people in these different fields and say, let's collaborate, let's somehow put our brains together and come up with something that maybe, and I don't want to be so arrogant to say it is better, but maybe might give us some improvements in what we do.
I know that in science, you don't do crystal ball gazing, but there will be a lot of people listening to this who, more or less all of us, know somebody who's suffering some dementia. So I suppose a burning question is, do you have any idea roughly on timescales when we might be living in a world where it's possible to start treating Alzheimer's pre-symptoms showing?
I think it is likely that over the course of the next few years that there will be the introduction of drugs that may be able to slow the disease. Why do I say that? Well, because there's a few trials being done around the world of these agents, these antibodies, trying to target these proteins, particularly there's one called amyloid. And the results of those trials are coming out and will be coming out over the next few months and years. There's already one that's been approved by the US federal FDA. That's not been as much of a success as people would have liked, but it's the first one of its kind to be licensed. The others that will come through will be better. So it's always creating a hostage of fortune answering this question, but I would say tentatively, I think we're going to see these drugs arrive over the course of the next few years.
The brain is fascinating. We're all wired differently. When you're making a cup of tea in your kitchen, we were talking about different parts of the brain. When you were studying medicine, what made you go into neurology, and what is it that fascinates you about this wonderful organ of ours that makes us who we are?
There's a philanthropist called Fred Kavli, a Norwegian philanthropist, and he set up a lot of institutes around the world to look at the three things that he thought were the most interesting things in the world right now. And they were the biggest, so cosmology, universe, astrophysics, the smallest, so high energy physics, particle physics, and the most complicated, the brain. And that resonates with me. These are the frontiers of science. Big stuff, you've got the small stuff, and you've got the most complicated thing in the world. The human brain is probably not a bad candidate for that. On a scientific level, I think for me, the brain has always been a fascinating realm to delve into. That's, I guess, as a clinician, that makes neurology the logical home for someone like me. And that's still as fulfilling now as it was at the beginning, because we are really at the beginnings of our journey into understanding the brain. We are so far away from really getting a grip into what this is all about and how it functions. We're sort of getting there, and that bit of the journey is really exciting, but there's an awful long way to go. But we can see how that might go in the future. We can see that actually the tools that are being developed now to look at how the brain cells work, not just as individual brain cells, but as networks of cells, that, all these new probes and devices and technologies that come out. I think over the next couple of decades, we're going to find our understanding of the brain is going to mushroom.
We were chatting about, I'm a creative person. I've been told by a neurologist that my time of greatest relaxation comes at the times when I'm adrenaline fueled. What parts of the brain will be developed for me to make me on that front?
To a certain extent, that's a nature-nurture question. So you will have a basic brain developed because of your DNA, because of your parents, because of the circumstances in which you were born. In other words, how many weeks your mother was at term for you, the circumstances and all that. In a crude way, your inherent brain hardware. Then that gets developed over time. You would have started off maybe with some strengths and weaknesses that are partly driven by the DNA you inherited. So that's that. That's your nature. But then your experiences through your early life would have then shaped that. And we know the developing brain changes a lot. So the kind of connections that we go between all our brain cells as we age, and by the way, that happens all the way into later life, so it doesn't stop. But the developing brain is certainly the most malleable, and that's when most of the connections will happen. So for whatever reason, you might not even know yourself because you might have been too little to remember, but those experiences will have shaped that sort of basic putty that you were born with. And for your particular circumstances as an individual, what that meant is that in adult life, you became more adrenaline fueled than others. And it probably was a concatenation of all these different events that linked back to not only the kind of person you were genetically the kind of brain you genetically inherited, as it were, but also your formative experiences. And then that feeds on itself, because if then you like something or you're good at something, then stands to reason you then do more of the same. And you end up as the adult you are now with the interests you have, which is different to me and different to anyone else that's listening.
What was it, do you think, growing up that made you lean towards medicine, neurology, the brain? What kind of kid were you?
I was a geek, so I kind of liked my science fiction. I liked my imagination. But I suppose also the way I was lucky enough to be in school, and particularly at university, particularly my PhD, I suppose the way I was always taught resonated with me, which was always question, always go back to first principles, don't take anything for granted, ask why. And I do remember from a very young age always just thinking, why? Sometimes there's some answers that you give, and sometimes people would invoke religion, sometimes people wouldn't, and there may be other things. But I do remember thinking, I want to understand this a little bit more. And so going to medicine is not about understanding why. Medicine is about, by no means slow, but I'm a medic. I'm inside the tent. I'm allowed to do these things. I can say these things. Medicine, you have to learn enormous amounts of information. And we do what we do because that's what works, and it's empirical. Medicine is not largely about why does this work. We give drugs because they kind of work. Sometimes we understand why they work. Often we don't. Or at least if we do, it's an incomplete understanding. But it's a practical discipline. It's a practical vocation. But that's not the same as a science question. The science question is the why. Why does the moon not fall out of the sky? Why do we converse the way we do? Why are you someone who likes skydiving, whereas me, I would never do that? You could give me $1 billion, I wouldn't do it. Why do you do that? Why don't I do that? And I don't know. But it's that why that actually I find intellectually challenging. And the idea of just asking the question, I think, is extremely stimulating. Having an answer, that'd be great. But if we don't have the answer, just asking the question at least takes you that bit further.
You are at one of the most intellectually stimulating places in the world in UCL. It has such an incredible reputation for attracting and nurturing some of the world's best minds. And I love that its tagline, disruptive thinking has been the status quo since 1826. Why do you like being part of UCL, Dennis?
I didn't know the tagline, so it's always I learn something new. It's an interesting dynamic between having a very, very large university with world-class people and a huge amount of infrastructure, and maybe a philosophy from the beginning. So its founder, Jeremy Bentham, one of the utilitarian philosophers in the 19th century, was always starting from fresh, trying to create a new academic environment when it was questioning everything and starting from first principles to some extent. And as a researcher, it's quite liberating because one doesn't ideally want to be constrained by dogma or tradition or practice or what was done before. But in a way, it can sometimes be more productive to challenge the status quo, to think differently. And these days, I guess the buzzword is disrupt. I think it's always slightly they're a bit too confrontational, that word, but I do understand what that means. But just to try to look at things in a different way and to develop new ideas or new processes or new diagnostics. And maybe that chimes with what UCL's founding principle was.
That sounds like it does. I do like that phrase. Disruptive thinking has been the status quo since 1826. It's quite inspiring. It is Dementia Awareness Week, and a lot of people will be very fascinated to hear the research that's going on, that you're doing, your colleagues are doing. So thank you, Dennis, for taking the time out to explain what's going on and really giving us an insight into what's happening in your world at the minute.
It's my pleasure. Thank you.
You've been listening to Dr. Dennis Chan from UCL talking about his neurological research work in the detection of Alzheimer's disease in its earliest stages prior to the onset of dementia. Today's chat, as I just mentioned, coincides with Dementia Action Week, which this year focuses on diagnosis. Don't forget to download and subscribe to our podcast series at convex.podbean.com or search The Convex Conversation on Spotify, Stitcher, Apple and Google Podcasts, or wherever you listen to yours. I'll be back next week with another fascinating guest, so join me then.